Hello, I'm Jamal-Odysseas Maaita. First of all, let me thank the organizing committee for inviting me to be a speaker on this very interesting and important conference for our community. I'm going to talk about the dynamical behavior of systems with a positive maximal Lyapunov exponent that is very close to zero. It is a work that I'm doing this last year. The idea came from the different approaches. I'm going to show you one I'm going to talk, the different approaches and the different conclusions that several scientists do when they calculate such values for the maximal Lyapunov characteristic exponents. In other words, the main question that I want to investigate and I want to try to answer is the following. Is a system with the positive maximal Lyapunov characteristic exponent that is very close to zero, for example, let's say 0.0001, is it chaotic or not? I will start my talk with some basic concepts for a dynamical system. First of all, we are talking about dynamical system. That means that we are talking about systems that evolve in time and can be represented by either ordinary differential equations, where we are talking about systems that we are interested in values that are continuous, that are changing continuously in time, for example, the speed of a car, or by maps when we are talking about systems that the time is discrete. That means that the quantity that we want to calculate changes not in a continuous time. For example, if we're talking about the population of fish in a lake, the number of the fish doesn't change in a continuous time. There are many parameters that play a role. For example, the duration of pregnancy, the number of deaths, and other things. So it's not important to know every second what happens, but we need something else. In general, the dynamical systems behave in three ways. The first way is to go away from a certain point. As we can see here, it starts from 0, and for 5 seconds it goes away from its initial point. Or the second behavior here is to tend to a certain point, to start oscillate, to start change, and then go and stop in a certain point for the time as time goes on. The second behavior is to have regular oscillations, that is to repeat even periodically or quasi-periodically, but to have a repeated movement, something that repeats. Here we see the periodical motion. Here we see the quasi-periodical motion. And the third case is to have an unregular oscillation, an unpredicted oscillation, the so-called chaotic motion. So obviously, the first case where the system is either explosive or goes to a certain place, there's it's not interesting. The system either doesn't exist anymore or stop of moving. The second and the third cases are interesting, both the regular and the irregular behavior. If the system behaves regularly, if there's a periodical or a quasi-periodically motion, so we can benefit from this behavior to have applications, to have engines and other things that we can use. And of course, when we have the chaotic, the unregular motion, even there we can use this motion, for example, in cryptography, or there are works even for the optimization of the motion of robots. And also, it's very important to study such behaviors to avoid undesirable behavior of systems that may be dangerous or anything else. So what is chaos? Let's start with some history. This is the picture of Henri Poincaré, that he was the first one that he found out while studying the three-body problem that there are several irregular orbits on this system. Other mathematicians also fell into this kind of irregular behavior. For example, Hadamard with his billiard, but they couldn't study and configure these irregular motions and irregular behavior because they didn't have the tools, the computers, to make the certain computations. So the development of computers opened this new window, gave us this opportunity, and here we have Edward Lorenz that back in the 1961, he was the first one that accidentally discovered chaotic motion, as we all know. So if we want to answer to this question, what is chaos? First of all, let's say that chaos can be seen either in systems with a dimension that larger than 3 nonlinear dynamical systems, or in simplest systems such as the logistic map that we have here. And as we all know, for R equals to 3.56995, the system has a chaotic behavior. So to answer the question, what is chaos, the most easiest configuration that we can say is the following, that chaos is the sensitive dependence on the initial conditions. If we want a more stricter definition, we can say that a map F is called chaotic in a complex invariant when it has a dense set of periodic orbits. When it is topologically transitive, that means that from any arbitrarily small region containing points of the invariant set, we may also visit other region that contains points of the invariant set. This property results in a mixing of the orbits under the mapping. And the third property is the one that we said before, that it has a sensitive dependence on initial condition. That is, in every regions of every point P of the set, there is at least one point P0 such that the orbits of the 2 points diverge a given fixed distance, independent of the starting point and the selected regions after finite steps. So, as we saw before, we can easily distinguish between regular, this is a periodic orbit here, and an unregular, this is a chaotic orbit here. But believe me, no scientist that works on nonlinear systems or chaotic behavior will ever tell you that this is a chaotic motion if didn't calculate that this is a chaotic motion. So we need more tools to investigate, to determine the chaotic behavior. There are several numerical and analytical tools. For example, the Melnikov theory that proves the existence of chaotic behavior, but it works for two-dimensional Leppertal systems with a shuttle and a homoclinic orbit. Obviously, this is a very certain kind of systems that Melnikov theory works on them. So there are many other tools, numerical tools that several investigators and scientists works. There's other methods. We are going to use the Lyapunov characteristic exponent and also the smaller alignment index. These are the two methods that I use here to investigate the dynamical behavior of the systems. So, as I said before, we are talking about the maximal Lyapunov characteristic exponent that has positive values that are very close to 0. So let's start with some basic notes on the maximal Lyapunov characteristic exponent. What the maximal Lyapunov characteristic exponent is, it calculates the exponential growth of two very close orbits, as we can see here. So here we see that there is this exponential growth. They start in a very close regions and they end in very different regions. And if that happens, so the system is chaotic. When this happens, when the exponent is positive. If there's at least one positive Lyapunov characteristic exponent, then the system has chaotic behavior. In other words, the system has a regular behavior. The good thing with Lyapunov characteristic exponents are that they can be calculated either in discrete maps or in continuous dynamical system in ODEs, and also we can calculate them for time series data. So there's a wide of applications, and most of the nonlinear scientists work with this numerical tool. Some properties of the Lyapunov characteristic exponents are the following. First of all, on each trajectory except equilibrium points, there is a Lyapunov characteristic exponent that is equal to 0. On damped system, if the trajectory starts from a point in the basis of attraction of an attractive equilibrium point, then all the Lyapunov characteristic exponents are negative. If it starts from a point in the basis of attractions of an attractive r-dimensional torus, then there are r Lyapunov characteristic exponents that are equal to 0 and the rest are negative. And if it starts from a point in the basis of attractions of a chaotic attractors, then there are one or more positive Lyapunov characteristic exponents. If it's one, then the system is chaotic. If we have more than one, then we say that the system is hyper chaotic. It is not an easy way to calculate the Lyapunov characteristic exponents. We need huge, long computational time, also big computational resources, but it is very simple and very easy to calculate the maximal Lyapunov characteristic exponent. And we can easily compute it by the following equation that we see here. Here we have the variational vectors, the W. So most of the scientists use this maximal exponent to calculate and see the behavior of the system. Let's go back to the main question of our talk today. What is the dynamical behavior of systems that have a maximal Lyapunov characteristic exponent very close to 0? As we saw before, the maximal Lyapunov characteristic exponent is when it is positive, then the system has an exponential growth, so it's chaotic. What happens when it is very close to 0? Is it really positive or is it 0? Is it chaotic or not? This is the main question. This is what we want to discuss and investigate here. And to do so, we used several systems, several different systems. But let's first of all discuss why we are asking this question. Here we see a book from Julian Sprott, published back in 2010, The Elegant Chaos. Julian Sprott is a scientist that worked a lot in the field of nonlinear dynamical systems and hydrogen interactors and chaotic systems. And here in his book, we see that he said that the practical computational difficulty is distinguishing an exponent of 0 from one that is small but non-zero. For the purpose of this book, values of the Lyapunov exponent for which the absolute value of lambda is less than 0.001 will be taken as 0. At the same time, in 2018, we see here a paper by Han, published in Chinese Journal of Physics by Elsevier, and we see here that for his, in his opinion, the 0.001 equals to 0. Also, 0.006 is a value that equals to 0. So we see here that there is different approaches from different scientists on how and what must take as 0 when we calculate the maximal Lyapunov characteristic exponent. So we want to discuss and see all these things. To do so, we take several systems for many different values of the initial conditions, for very different values of the parameters, and do the following. First of all, we are talking about three-dimensional systems, and we wanted to study them with the help of the smaller aligned index. We use this index because it's different than the maximal Lyapunov characteristic exponent. I'm going to show in a while what is the difference between the two indices. Also, we take the Poincare maps and the phase portraits, the trajectories, the orbits that show us what is the behavior of the system. So let's say some words about the smaller alignment index, some notes about it. First of all, it was introduced by Haris Kokos back in 2001. Haris Kokos is a well-known scientist in the field of nonlinear science. And he is one of the speakers here in our conference, in the International Conference on Nonlinear Science and Complexity. This is a very good index with very good results, and uses another different than the maximal Lyapunov characteristic exponent. It utilizes the property of the chaotic trajectories that two variational deviational vectors corresponding to two different Lyapunov exponents, lambda1 and lambda2, eventually align. What it means that eventually align, that means that they start, as we see here, and after a while, the trajectories, the two vectors, the two variational vectors, become closer to each other, or they have a very close angle, about 0, or they can go to a 180 degrees angle between them. So if we want to configure SALI, we configured it by the following equation. We take the minimum values between the addition of the two normalized variational vectors, or the difference of these two normalized variational vectors that we have here. Some properties of the alignment of the smaller alignment index are the following. First of all, the smaller alignment index tends exponentially to 0 for chaotic orbits. For regular orbits, takes constant values different than 0. It attains values in a given interval between 0 and the square root of 2, and it works on both Hamiltonian and dissipative systems. So let's go back to the main work of this investigations. Let's see the numerical results. First of all, we use this first system. It was introduced by Clinton Sprott back in 2010 in his book Elegant Chaos. It is a three-dimensional system with an hyperbolic sinus here. As you see, I use this parameter alpha here to change the systems, and I calculate the maximal Lyapunov characteristic exponent and the smaller alignment index. So as we see here, for values of 0.0024 larger than 0.001, the smaller alignment index is 0, so it tends to 0 exponentially, and we have a system that is chaotic. For values as here, that is 0.0000056, the SALI is not 0, so the orbit is regular. And also we can see that for values small as here, we have some values that tends to 0, but are not exactly 0. So we use the second system. This is also a system introduced by Julian Sprott in his book An Elegant Chaos. It has a hyperbolic cosinus here. Here we have the same parameter alpha as before. We took different values. Here we see that also for 0023, it is a chaotic system. 0001, it is the 10 minus 5, as we can see here. There are some other values for the initial conditions. Of course, these are not all the initial conditions that we took, but there are some of them. The third system is also introduced by Sprott back in 1994 in his paper, Some Simple Chaotic Flows, published in Physical Review E. We see here that the parameter alpha is in the nonlinear term with psi. Here we took some values, as we see here, for values like 0.013, the system is chaotic, as we know, and as we were, it was our prediction that will be. We were expecting this behavior. And the fourth system is a system with a cubic nonlinear nonlinearity and no equilibrium points that was introduced by me, Professor Volos, Professor Kyprianidis, and Yannis Stoubulos back in 2015. Here we see this term alpha that makes the system to be with no equilibrium points. And we see also the different values of the Sally and the maximal Lyapunov characteristic exponent. To conclude, let's go to the discussion. First of all, as we saw before, when the values of maximal Lyapunov characteristic exponent are larger than 0.001, then the smaller alignment index is 0, tends exponential to 0, the system is chaotic, and everything is very clear. We can see here, for example, that for 0.008, this behavior of the Sally, the exponential goes to 0. These are log and log values here. Also, we can see the Poincare section of the system. It is taken for the last 1000 time units. And there are the phase portraits of the system that we can see that it is obvious that it has a complicated and a chaotic behavior. The second clear thing in our work is that for maximal Lyapunov characteristic exponents that are less than 10 powered minus 4, the Sally is not 0, so the system is regular. Here we see that, for example, for 0.00005, the Sally oscillates in a region that it is about 0.00255. It doesn't growth exponentially to 0, so it is a regular orbit. Here we see the Poincare section and also the phase portraits of the above values of the above orbits. And what is interesting is what happens between 10 powered to minus 4 and 10 powered to minus 3. There, as we saw before, it's not something that we can clearly speak about. For example, we saw before that there were some values that it wasn't 0. Here we see a value, for example, for 0.00037, that this, for these values, the Sally tends to 0. So it seems that it is a chaotic orbit. We can see here that with the Poincare section, it doesn't really look like a chaotic section. Maybe it is an attractor or something, but we cannot be sure of it. And also, we can see this behavior in the phase portrait. So, to close, let's see some what we need to do in our next steps. As I said before, this work is done these days. I'm working on it on these days. So, what I'm talking about is not final conclusions, are some thoughts, and I will be happy to hear your thoughts on what I'm presenting today. So next steps must be to have more computations for values on this interesting area between the power of minus 4 and minus 3. Also, we need to investigate more systems. We have done some work on more systems than the above 4. And also to check the possibility of transient chaotic behavior that may trap the Sally in these cases for these values of the maximal Lyapunov characteristic exponents. So this is it. This is the end. Thank you for your attention. And this is the my website and also my email. And as I said before, I would be happy to hear your notes, your remarks on what I presented today. Thank you very much. Thank you very much.